For this problem, we're going to use conjunctions because the intersection of sets is involved, and we're also going to use a biconditional because the equality of sets is involved. Here's the statement. Prove that for any sets A and B, the power set of A intersect B is equal to the intersection of the power set of A with the power set of B. So the reason this seems true is if we look at a couple sets A and B, then an element of the left side here is a subset of the intersection. Maybe I'll call it S. Whereas an element of the right side it has to be a subset of A and a subset of B. Okay? If you think about it, being a subset of A and a subset of B at the same time is equivalent to being a subset of the intersection of A and B. So that's what we want to prove. It's going to take a little bit of work though. So here is our goal. For all A, for all B, this equation is true. And the first thing we like to do is just let A and B be arbitrary, which looks like dropping the quantifiers from the statement. And then the definition of two sets being equal is that for all S being in the left side is true if and only if S is in the right side of the equation. Okay. So that's what we need to prove. And well, we can let S be arbitrary and drop that quantifier. And then we have to prove the two directions of this biconditional. So let's do the first direction, the sort of left to right direction first. To prove that conditional statement, we take the antecedent as a given. And then our goal is that S is in the intersection of a couple sets. And being in the intersection means that you have to be in both of them. Right? So S is in power set of A and it's in the power set of B. And then we have a whole bunch of elements of power sets here, and being an element of a power set just means that you are a subset of that set. So S is a subset of A intersect B, S is a subset of A, and S is a subset of B, are what we get. And now we've got a conditional over in our goal, so let's just split that up into two goals. And now we have a bunch of subset statements. And we can write out the definitions of those. So remember, for S to be a subset of A intersect B means there exists some X such that X in S implies X in A intersect B. And similarly for these other two statements. Right, so did I say there exists an X back there? I meant for all X. Okay. Now we have universal statements as goals, so we can let X be arbitrary and drop the quantifier in each case. And now we have conditional statements as goals. And the nice thing is they happen to have the same antecedent. So in proving each of those, we're going to take X in S as a new given. Okay. And then we have these two consequents as our new goals. And we can do a universal instantiation to get this statement for the particular X that we're dealing with here, which is good. And then we have modus ponens, from which we can conclude that X is in A intersect B. And that gets us our goal, because that means X is in A and X is in B. And that's what we wanted. Okay, so we still have to do the right to left direction of that biconditional, but let's pause here and write up what we have so far. So the first thing we did was to let A and B be arbitrary so that we could drop those universal quantifiers and arrive at this new goal. So I'll say let A and B be arbitrary, and those are sets. I'll mention that. And then we use the definition of equality of sets to get here, and we want to drop this quantifier, so we will also let S be an arbitrary set. And I probably wouldn't put that sentence in my proof if I were writing this, but for completeness it's not a bad idea when we're starting out. Okay, and then after we drop that quantifier, we get this biconditional as our goal. So we should say where we're headed. So we show that That is true. Okay, good. Now we head on to the left to right conditional statement, and we take the antecedent as a given, which gives us this goal. And you know, right away when people see that S is in the power set, we want to think of that as just S being a subset of A intersect B, right? And same thing here. If S is in these two power sets, then excuse me, yeah, it's in the intersection, then it's in both power sets, and so in particular, S is a subset of A and S is a subset of B. Okay. So let's, first of all, people like to put a little forwards arrow in parentheses sometimes to indicate that we're going to prove that direction first. And then we can say, suppose S is in the power set of A intersect B, which remember means that S is a subset of A intersect B. So I'll say that is S is a subset of A intersect B. And then our goal now is we're going to show that S is in the power set of A intersect the power set of B. There we go. Or equivalently, that S is a subset of A and S is a subset of B. Okay, so that's what we need to show, those two things. And then what happened next? To prove these two statements, we write out the definitions, and then we can let X be arbitrary for each of them to get these conditional statements as goals. And conveniently enough, they have the same antecedent, and so we make that a given, which leaves us with these two goals. All right, so maybe that can all go together here. We want to say let X be arbitrary, right? But then in the same breath, we want to say that it's in S, and so we'll say let X be an arbitrary element of S, and we are going to show that X is in A and X is in B. Perfect. So to finish things up, we had a modus ponens lurking here, and this conditional came from here, which came from our subset statement, right? And together they give us that X is in A intersect B. So I'll say because X is in S and S is a subset of A intersect B, it follows that X is in A intersect B as well. And then to finish up, you know, what does that mean? It means that X is in A and X is in B, which was our goal. So I'll just say equivalently X is in A and X is in B. Okay, that's what we said we were going to show. So that finishes that direction of the proof. And now we're going to come and do the right to left direction. Okay. So there's our goal, and we can bring our antecedent over as given, and we have that S is an intersection of two sets, which means that it's in the first one and in the second one. And then we have that S is in a bunch of power sets, and we can replace those by we can break up the conjunction into two statements, and now we can say that being in the power set is the same thing as being a subset of A, B, or A intersect B. And then we can write out definitions of our subset statements, and then we can let X be arbitrary, so we drop our universal quantifier. And to prove this conditional, we can let its antecedent become a given. And then we can do some universal instantiation to get these statements for this particular X and S that we're dealing with. And then we have a couple modus ponenses. Is that the plural? Modus ponens lurking here. That one gives us x in A, and this one gives us x in B. And together, well, x in A intersect B means we want to find that x is in A and x is in B, and that's exactly what we have. Okay. So let's write this one down. First of all, we took that as a given, and we want to prove this. And just like before, let's sort of immediately comment that that statement is equivalent to these two, and this goal is equivalent to that one. Okay. So I'll say suppose S is in power set of A intersect power set of B, or equivalently that S is a subset of A and S is a subset of B. And then for our goal, we're going to show that that S is in power set of A intersect B. That is, that S is a subset of A intersect B. Okay, and then let's see, we wrote out definitions, and we want to let x be arbitrary to get this goal, and then at the same time we want to say that x is going to have to be an S, okay, to get that goal. So we can say, once again, let x be an arbitrary element of S, and we're going to show that x is in A intersect B. And finally, we got to put all our givens together. So because x is an S, and this conditional, which came from S being a subset of A, we can conclude that x is an A. Because x is an S and S is a subset of A, it follows that x is an A. And we can do the same thing to get with this other conditional, which came from S in B to arrive at x in B. So because x is an S and S is a subset of B, it follows that x is in B. And finally, we should just say that that's what we were going for, right? That because x is in A and x is in B, we have that x is in the intersection of the two. Okay, so let's say because x is in A and x is in B, it follows that x is in A intersect B, which was our goal. And we're finished.